Deep inside the sun's core, something extraordinary is happening right now. Billions of particles are being born every second. They escape instantly, racing outward at nearly the speed of light, completely unaffected by the crushing pressure and heat around them. Those particles are neutrinos. And for the first time in history, humanity has sent a specialized detector into space to catch them. On May 3rd, a small spacecraft no larger than a shoebox launched aboard a SpaceX rideshare mission from Vandenberg Space Force Base in California. Its name is SNAPPY, and it represents a fundamentally new way of looking at the universe. For decades, neutrino physics has relied on a single strategy: build massive underground detectors, bury them miles beneath the Earth's surface. Scientists do this because our planet is bombarded by cosmic rays that create background noise, drowning out the faint signals they're trying to detect. China's Jiangmen Underground Neutrino Observatory sits 2,300 feet below ground. The ice cube detector at the South Pole is embedded in ice between 4,750 and 8,040 feet deep. These are engineering marvels. They work. But they are limited by their fundamental constraint. They are stuck on Earth. That constraint inspired physicist Nicholas Solomé at Wichita State University to ask a radical question. What if you didn't need to dig deeper? What if you moved closer instead? Moving closer to the sun changes everything. Neutrinos streaming from the solar core become dramatically more abundant. A 1-kilogram detector positioned near the sun would receive as many neutrinos as a 1,000-kilogram detector here on Earth. That density difference means you can detect signals from space that would be invisible on the surface. But first, you need to prove the concept works. That's what SNAPPY does. The detector itself is remarkably small. It consists of just 4 crystals made of gallium and tungsten. These crystals are the size of your hand, weighing around half a pound total. They're encased in a protective shielding block made of epoxy loaded with tungsten dust. The entire assembly fits into a 3U cubesat, a standardized satellite platform measuring about 12 inches long and 4 inches wide. Inside that compact frame sits not just the detector, but a dedicated electronic suite designed to record and analyze every particle collision. The satellite launched into orbit at an altitude of 310 miles above Earth's surface. From that vantage point, it has an unobstructed view of the entire sky that matters more than you might think. SNAPPY isn't just meant to study the sun, it's meant to watch the universe. When a massive star collapses at the end of its life, it produces a supernova. That catastrophic explosion happens in less than a second. But before the light reaches Earth, something else happens. A burst of neutrinos, dozens of them, streams out from the dying star's core. A detector in space, unhindered by Earth's atmosphere, could catch that burst. Scientists could measure it. And from those measurements, they could reconstruct what actually happened at the moment of stellar death. That information would arrive faster and carry more detail than any telescope could provide. The electronics powering SNAPPY are projected to remain operational for approximately 3 years, but the spacecraft itself is designed to remain in orbit for 7 years. That gives scientists time to validate the core technology, to prove that space-based neutrino detection isn't just theoretically possible, it's practically viable. This mission is the proof of concept. It's a small step, but if it succeeds, the next step would be far more ambitious. A dedicated spacecraft launched closer to the sun could carry a larger detector array. It could observe solar neutrinos in unprecedented detail, revealing secrets about the sun's fusion processes that can't be studied any other way. It could watch for stellar collapses throughout the galaxy. It could fundamentally change how we understand the universe at its most violent and most fundamental level. For now, SNAPPY orbits above us, 4 small crystals embedded in a shoebox. A microscope pointed at the sun's core, and the beginning of a new era in space-based particle physics.